All right, so we'll get going before I hand it off to Austin. Again, thanks everyone for joining. We're doing a webinar on a guide to understanding SWIR applications. For those of you who don't know me, my name is Paul Preuss. I am the product manager here at Metaphase, so deal with all things that do with the product line, and always looking for customer feedback and anything we can do to make the product line better. For those of you who don't know Metaphase Technologies, we've been in business for about 27 years. We specialize in all aspects of machine vision LED lighting, and we pride ourselves on being somebody who can provide custom solutions and really being a solution provider for anything in the realm of machine vision LED lights. I want to start with some housekeeping rules for the webinar. We're going to be doing about a 20-minute presentation. The session is being recorded. Anyone who's registered will receive an email within about 2 days of the webinar with a link to the recording so you can view it. And then if you have any questions, there's a Q&A link on the bottom where you're able to type a question in. We'll get to as many questions as we can at the end. And if we don't get to any questions, we'll email you about that afterwards. All right. And next slide, just introduce the speaker. All right, and Austin O'Neill will be giving the presentation on SWIR, and he is one of our application engineers there. He's the person in the lab who you send your products to be tested. We have a full application engineering lab where we find solutions for our customers, and we also have eval lights that we send out. So he's the person on the other side of the email that you often send things to, and he's prepared this presentation for us. And with that, I'm going to turn it over to Austin. And Austin, thank you.
All right, thanks, Paul. And once again, I want to thank everyone on behalf of Metaphase for joining us today. I'm very excited to be able to talk to everyone the next couple of minutes, next half hour about SWIR and understanding it a little bit better, as it is an emerging part of our machine vision industry, and it is going to be a huge factor going forward. Just kind of setting the ground a bit, we're going to first go over understanding what actually shortwave is, SWIR, and how that fits into our current interpretation and what part of the spectrum we incorporate on a daily basis across the machine vision industry. And through this, we can become familiar, not only familiar with the industries that are being currently using this, as well as the applications that are able to successfully leverage SWIR in their applications. And because of that, there are certain hardware considerations that have to be accounted for, so that way you have no bottlenecks, that you're still able to achieve very high contrast levels on your particular part. And across the board, we'll also be talking about, there are some caveats and application considerations you need to do when incorporating with SWIR. But with that, we'll get started and with our electromagnetic spectrum. And for those of you who may or may not be familiar or have learned this in a high school physics class, all light is a part of the electromagnetic spectrum. And what this means is the light that not only our human eyes see, but as well as our machine vision cameras exists as a very small subsection of this larger spectrum. This incorporates every type of wave across the board, from things such as radio waves, TV waves, all the way up to X-rays, as well as gamma rays. This part of the section is incredibly small, but the part that we refer to as visible light is typically around 400 to about 780 nanometers. This can vary depending on who you're referring to, but for the most part, red, green, blue, and all the other colors that make up this are all in this very narrow part of this huge spectrum. Below that, in the visible, we do have the UV, and that can have its different UVA, UVB, and UVC. But we're going to be focusing on in today's presentation, above that, around 780, which is considered to be shortwave infrared. And specifically, even higher up is where this part of the spectrum that we are actually interested in. So infrared light is
usually... Sorry to interrupt. Could you just go into presentation mode and make it a little bit bigger for everybody? So we're just getting a little comments, it's a little bit small. I think you're in the speaker mode.
Is that better?
That's it. Yep, perfect. Sorry. Thank you. Go ahead. My apologies.
So infrared light is typically is going to go from about 900 to about 1700 nanometers. And this is very similar to the visible light that in the same way that it interacts optically. We're really focusing on emission and absorption levels. Emission being things that materials can, certain spectra are emitting with certain energy, and absorption is the resulting of receiving that energy. Now, infrared light as a whole does have its pros and cons. One of the pros being, though, compared to systems that are currently being used for SWIR systems, such as halogen or X-ray, you can have a much lower cost of entry and reduce the hazards of working with it, as well as the maintenance needed to maintain those specific systems. The cons being that can be limitations with your resolution as compared to regular machine vision, a higher cost platform, but we'll get into those throughout the rest of the presentation. So going into the industries that are using this, we're going to understand that the big one that many people might be familiar with is going to be military defense and security operations. If you've ever tuned in to a newscast watching footage from a military operation, you might see an image similar to the one that you're looking up here in the top left. That image is really useful because even at night or during the daytime, independent of any type of terrain, the individuals on the ground can get a very good sense without giving out their position. And it is a very common use of this. Another one being similar related to that is satellite imagery. On the photo here on the left, you'll actually notice is a wildfire over a given area, and that there is a lot of amount of smoke, which can make it very difficult to see where exactly that fire is centered at and where it is spreading to. Having satellite imagery using SWIR technology allows people on the ground and to analyze this area and understand where the fire is and where it's concentrated at, which is invaluable information for first responders on the ground, so that they can quickly and efficiently put out the fire. Now, with that too is another one that is really popular is our agricultural. Now, this begins to show the benefits of SWIR, as SWIR really does a very good job at observing certain types of carbon-based life forms and biological samples as well. The photo on the left seems to be a perfectly good looking apple. This is something that would pass most inspection systems. What we ended up seeing here on the right, though, is there's a higher concentration of contrast, which is actually being produced by more water, aka bruising inside that fruit. Now, this is one example of how SWIR allows us to see things that our human eye and machine visions can't see, which is crucial for quality control and quality assurance of given products, especially within the manufacturing space, which is what some of these other applications go into as well. So a very common one that I see on a daily basis is going to be fill levels. And on the left here, in the top left, you'll notice a photo of a generic laundry detergent bottle. This bottle is a very opaque, semi-reflective type of plastic. And as it is making its way through the production line, it can be very difficult to ensure proper fill levels have been obtained. But having a SWIR system easily allows us to identify where that fill level is and ensure that that passes or fails given on the given criteria that the manufacturer or the plant has. Now, similarly, there is also related to this is liquid detection. And if you look at the bottom here, you'll notice 4 vials, which all look very similar to one another as a very clear sort of type of solution. Now, although my background is in physics, I can assure you I would not want to drink any of these 3 but water. And given that under SWIR lights, we can easily identify the contrast levels between each of these, and knowing the atomic and chemical properties of these, we can easily identify these to ensure that the proper ones are being used in certain experiments. Now, one that some people might be familiar with also is this photo is one of a United States $100 bill featuring one of the founding fathers. This has a lot of security measures, not only from watermarks to holographic inlays, but as well as certain markers too. And I want to bring your attention to a smaller section to the right of that strip, which looks like a jug under normal lighting conditions. When switching to SWIR, you'll notice that it becomes a bell shape, further enhancing the security and preventing from other people being able to copy this and reproduce American currency or even other types of currency. This is also being used to authenticate art in a non-invasive way, as it allows galleries and whatnot to be able to see the different layers of a paint and understand that it was attributed to that original artist. Now, as we're also going through some of these other ones, material analysis is a very crucial one. Similar to the solutions that we saw earlier, this is a sample of a pharmaceutical application where we have two vials. One is some sort of aqueous solution and another one with this rubber cap on the left. Under normal condition, this looks clear and it'd be hard to identify what this is. Having the advantage of SWIR in this part allows us to see that that liquid would be more akin to something like a water compared to the other substances. And we can also see on that button, it does say paralyzing agent, which is due to how there is a plastic cap above this. We're able to do optical character recognition. And this goes back to the whole idea of absorption, and that certain of these wavelengths across the SWIR spectrum can penetrate through different sorts of films to be able to see something and really enhance a quality inspection system. Now, similar to that, though, is anything with paints, adhesives, and caulks. And this is very valuable for being able to image things without having to add additives such as whatnot. Normally, if you'd have some sort of adhesive, you might put some UV dopant in that. From a manufacturer standpoint, that can be an expensive process to be able to implement properly. The benefit of SWIR is that you can differentiate this without having to add UV dopants, which significantly brings down the cost of your whole system. And because of that, it can make it cheaper to produce, and thus lowering your overall cost, making up for the higher cost of the whole system in general. This photo here that you'll notice is a photos of three types of paint over some type of image that you can't really read. The SWIR system completely eliminates any type of paint, allowing you to easily identify those characters and do any sort of optical character recognition, as well as optical vision recognition as well. Now, a more popular one too is we're going to see, especially in these days and age, is semiconductor wafer inspection. Typically, what the photo you're noticing here is a wafer, and the typical response for this one was from about 1300 nanometers to 1550 nanometers. And this is really important for semiconductor manufacturers to be able to identify dust and voids in coatings. In fact, the amount of co-eccentric rings that you see on these defects actually allow the manufacturer to know what specific level that defect is actually coming from, similar to rings on a tree, like you would to determine the age. Now, switching, after now understanding the application side of things and why it is important and where these things can be used, I want to now talk about the three main key parts to any machine vision application. And that is going to be your camera, your lens, and your light. Without any of these three, you're going to have a very difficult time, if not impossible, producing accurate contrast and identifying the features for any sort of imaging process down the line, downstream, to be able to properly utilize this system. So in regards to cameras, we are going to have to talk about the spectral response, or also known as quantum efficiency, of different types of sensors, and why is that if you are trying to implement a SWIR application, the importance of using a sensor that can actually see the wavelengths you are trying to either absorb or emit. And partnering that with your camera is important to also think about the type of lensing you use. Not all lensing is made the same, and most machine vision lenses would actually for later reasons why you'll see, block these certain wavelengths, really inhibiting your overall relative illumination throughout your whole system. And additionally, especially because in the shortwave infrared, a lot of these things aren't naturally emitting these wavelengths, which is why you need lights to either properly provide that energy for emission or absorption to be able to see through different layers, like you would in a given rubber ball or something like that. And the lights, depending on the application, can vary from as one wavelength to something that is multiple wavelengths or something that is even hyperspectral. But going to the camera side of things, as you may or may not know, most machine vision based CCD as well as CMOS sensors use silicon-based chipsets. This works great across the visible range and even extends a little bit into the near infrared as well as the UV. This allows for very high amounts of illumination, but what you'll notice in the next slide, when we'll see that this really falls off around 800 to about 1,000 nanometers. So really any sort of analysis being done after that fact is going to have to utilize a SWIR camera. Now for SWIR cameras, you do have two options that are currently available. And the most common one is referred to as an InGaAs sensor, which stands for an indium gallium arsenide type of sensor. This provides much higher contrast values above 1,000 nanometers, which allows you to make sure that you have that. There are some limitations though with this sort of system, but you still have the same type of options in terms of area and line variance, just like you would have on silicon-based chipsets. Though where the limitations do start to comes into your resolution. And that is because of something, at least here in the United States, referred to as the International Traffic in Arms Regulations, or ITAR compliance. What this basically says is that things or processes or products used for defense purposes have to be closely regulated on the technology who's available and the manufacturers that can produce that. Because of that, the resolution considerations on an area scan, you're going to find much smaller resolution compared to your normal CCD and CMOS sensors in the visible. Typically, for area scanned, you're going to be limited to about 640 by 480 resolution, which is technically VGA. Now, that is one benefit of this emerging technology referred to as quantum dot, which we have seen make waves in this industry over the last 5 years, is that quantum dot isn't attributed or under the same type of regulations as you would for ITAR compliance devices. The benefit of this is that we have access to much higher sensor resolutions, although it does come at the effect where you're going to need a lot more light due to the limiting quantum efficiency of your sensor. And this chart just shows emphasizes the importance of choosing the proper camera for this. You'll notice on a silicon CCD or even a CMOS array, you have great spectral performance across the visible, even up to the early stages of the IR. But you'll notice right around 900, you're going to see a significant drop of about 20% quantum efficiency. This means the photons are only saturating about 20% of the wells in your sensor, resulting in a lot more light required to achieve the same levels. Switching to an InGaAs, you'll see you have about 80% quantum efficiency across the entire SWIR spectrum. This allows for high contrast and high level of accuracy and without needing a lot of light as you would with a typical silicon array. Now, with any camera, you're obviously going to need to account for your lensing as well. Most standard machine vision lenses, whether you're using a monochromatic or a color camera, are going to use a basic either anti-reflective coating, such as something like a magnesium fluoride, or potentially even something that is a little bit more broad spectrum, such as a visible NIR. Now, this is super important to know what type of analysis and what wavelengths that you need, as if you're looking at an application that really needs to use 1200 nanometer light, you're going to notice, depending on the vendor who you get your lensing from, you may have to have a different coating. So it is important to take that in consideration because we want to make sure sure none of our components are going to be bottlenecking each other and allowing the most amount of light to pass through our system to perform easier analysis and image processing. Now, because of, as I mentioned before, the IR is not visible to the human eye, this can make aspects of alignment, especially with line scan, particularly challenging. Because of this, there are several manufacturers and companies who make alignment tools and wands that allow you to see at least the path of your optical axis to make sure you are that your lens is centered on your region of interest. And doing any sort of high-level lens or even optical simulation, you need to make sure that your ray tracing accounts for these types of wavelengths, as certain wavelengths are going to be focused slightly different depending on the material, coating, and composition, as well as design of that particular lens. Now, the last part of this triad needed for applications is going to be lighting. And for those of you who are not familiar with Metaphase, we provide SWIR illumination systems for 6 discrete wavelengths across a lot of our products, which includes things such as line scans lights. And for those of you familiar, these are our product lines such as our UL line lights, as well as our MB collimated and uncollimated line lights, as well as diffuse lighting. This is your ring lights, your dome lights, your flat domes, backlights, things such as our Meta Bright backlight, as well as our brand new TX backlight that can have this technology. Front lighting, 2 examples of this are our EXO or our ISO lines of lights. And across all of these products, you can typically find monochromatic, multispectral, or hyperspectral options. And what that means is that if you're interested in a particular either one wavelength, let's say you just want to use 1050 nanometers, you can just have a light with that, or maybe you need 3 discrete wavelengths for 3 different types of defects, or potentially you need something ranging from about 1050 nanometers all the way up to 650, producing a very broad spectrum like you would in the visible with white light. And just like any lighting option, they are available in large ranges of sizes and configurations depending on your specific application needs. And this is just one example of a hyperspectral curve generated using a SWIR-based camera system. You'll notice that there are dips and valleys, but this is something that if you know you need less of one wavelength and more of another, typically we can make at least for Metaphase, can make a custom output for your spectral to get better enhanced and give you the relative intensity that you need for specific wavelengths. Now, it's hard to believe it's already been 20 minutes, but as we're wrapping up here, again, want to thank everyone for joining us today, and we will be sure to answer as many questions as possible. I want to leave everyone with some takeaways that are really important to keep in mind when going into SWIR or understanding how to use SWIR applications. First off, this is going to give us a better fundamental understanding and a wider breadth of wavelengths available to us to use for different applications. What this results in is that it becomes another tool in the toolbox for applications. Not all applications have to start with SWIR unless you specifically know your material or your process, or that's one of your requirements from your customers. I would still go through the typical routine of starting with a visible light. If it was a sample I knew nothing about, I would start with the visible light. If that proved to be unsuccessful, I would then switch to something in the UV. And at that case, now I know that those applications that you might have dismissed or thought were impossible are now accessible or could be accessible because of the opportunity unlocks by using SWIR lighting. But to keep in mind is if you are going to use SWIR lighting, you do have to account for the proper hardware, and your distributor or manufacturer or integrator would be happy to walk you through that to ensure that you have system-wide compatibility and making sure that there's no bottlenecking, that you are able to see your defects and see them with enough contrast to be able to produce image processing. But at the end of the day, SWIR is all about being able to see the invisible. SWIR isn't visible to the human eye, but there's so much more information out there that can be accessible to machine vision applications that can prove invaluable for not only quality inspection, but as well as material analysis, from silicon wafers to agricultural products like fruit. But at the end of the day, seeing isn't always believing, especially since SWIR gives us access to outside the visible spectrum by providing light beyond the visible. And once again, I'd like to thank everyone for attending today. We will, like I said, if you do have to drop off, I understand. We'll be taking questions as long as there are some. And here's our contact information if you need to reach us. And once again, I appreciate for everyone's time, and thank you to Paul and everyone who's attended for participating in this. And I think we're going to start. Paul, I think we have some questions, correct?
Yes, we got a few coming in, and if anyone has any more, there's a Q&A at the bottom there. You can just type your question in as we're going through these. Thanks, Austin. It was great, informative, really great presentation. Appreciate it. And as he said, our contact information is there. If you need anything from the application engineering team, please reach out to him. And for those of you who haven't met me, please feel free to drop me an email if you want to get on a quick webinar or web call to just discuss some things. Always happy to take some feedback or let you know where we're going with some of the new products. So please reach out. All right. So.
Yep. Go ahead, Paul.
Do you have anything else?
Nope.
All right. So let's see. First one we have. Somebody said this is very interesting and makes me think of X-ray technology, which leads me to the question: is SWIR imaging safe?
Yeah, so like with any type of lighting or parts of an application, you always need to take proper safety precaution. You need to take proper precautions to ensure that you're not only technicians, but integrators are staying safe. This does provide a low barrier of much safer compared to X-ray systems, but you still need to account for the safety of the output of the light, similar to like you would for any other part from UV to visible, and that is testing information that can be provided for that.
Okay, so, and I kind of seems similar to that. Is SWIR safe to the skin and eyes? Are there any special precautions needed, such as a shrouding in the inspection area? It's kind of
it really. Yeah, it really, I mean, just to comment on that, it really does depend on what type of light or application you're needing. Ideally, you're going to want to shroud anyway, just to eliminate just stray light from entering your application, which can be very damaging to certain types of inspection. SWIR lights do fall under the same category as IE standards for risk group testing, and the same of UV, and that they're done in the same way. Certain wavelengths are going to provide higher hazard function, but Metaphase does have the ability to be able to test for that and provide that information if needed. I think we have some questions coming in live. I don't know if you're seeing. Do we have demo hardware for various SWIR wavelengths? Yes. So in-house here, I am on location at our Bristol site in Pennsylvania. We do have not only access to SWIR lenses, SWIR's cameras, but in terms of demo lights, we have plenty of the formats mentioned before that we would be happy to use as evaluation units or demos for your testing. And I'd highly encourage you get in contact with us to be able to facilitate that, as we have all wavelengths across of all different types of light to really help you fine tune not only what wavelength you're going to need, but also what type of light you're going to need.
You. We also have, let me see, another one here. Can you get polarization with SWIR lights?
Yes, you can. So, and that's actually one. You don't have to worry about hot spotting from ambient lighting as you would with other applications. Yes, SWIR polarization does exist, and there is a higher bar of entry for implementing that. I have personally not seen too many applications that are also polarizing SWIR, but it is certainly possible. And if there's a specific thing that you think you might have to polarize that, we'd love to talk to you about that. But yeah, it is an option, but it is more dealing with cutting down the reflections and whatnot. And because of SWIR cannot be seen, you don't have to deal with as much of interference from other outside sources.
Great. And you did mention how the some of the pricing was coming down on stuff. But that's always something to consider. So, any information about the SWIR camera prices coming down?
Yes.
Or is
So like I
less
said,
expensive?
I mean, it should be no secret that SWIR, I think, as a commercially viable application for machine vision solutions is certainly still in its infancy, is not as developed as other machine vision systems and cameras. I mean, yes, it has come down significantly, and that's due to advances in manufacturing as well as other new technology like quantum dot. There is, like I said, a much higher entry, but like I said, in things of, if you're looking at certain types of adhesives where the only alternative would be to add a UV dopant, the cost may justify having a higher end system. Typically, though, I would recommend, if you do have the flexibility between an area or a line scan system, I would highly recommend a line scan. This is because not only does the camera have less physical cells, but also the light is going to have a lot less light, lowering your cost overall. We looked, there are reports, to say within the next 5 to 10 years that it is going to become more of a entry level process, something that we even seen for those of you who attended the Vision Show in Stuttgart, as SWIR is going to be a presence and certainly a huge factor going forward within this industry. But that's a fantastic question.
Okay, great, thank you. And as I said, there's the Q&A at the bottom. It's near the chat. It's a little bit different than a normal Zoom meeting, so to make sure if you have any trouble finding it, it's at the bottom next to chat, says Q&A. Still have a few more rolling in. Are there any absorption spectral curves for different materials to help determine how an object might react to SWIR without actually having to test it?
That, I mean, again, really largely depends on what your application or what your material is. If you're working something with a raw material, like I said, there's carbon-based, agriculturally based, or even just a raw material such as a certain type of mineral, that information is well documented and well cataloged and can easily be accessible. If you're dealing with something that is more of a manufactured process, something like a rubber or different layers in a certain type of ball, that is something where you're going to need definitely either if your company doesn't have access to material sciences, which most don't, is really at that point becomes a trial and error phase. And that's the benefit of having access to the equipment and all the lights, is sometimes you might have a thing work really well at 1200 nanometers, but it's not going to work so well at 1400. And that's something that's best of, getting a sample and just starting to play around with it. So it really depends. Like I said, some of the more natural things are easier, but it really just also depends if you're also trying to have SWIR absorb, or if the material's more going to be emitting that energy back.
Okay. Someone asking if you could go back to the vial cap that you were showing. Interested in
Yeah,
that.
certainly.
We're saying, are you saying that the print on the metal stopper cap is only visible using SWIR?
Yeah, so again, I wasn't directly on this application, and specifically as one of my colleagues, but for the most part, this part here on the let me pull up a laser pointer. This part here on the left is typically a one-time use thing. So using a vial, you would take off this cap, and this would be like a metallic foil, which you'd actually puncture in for the syringe or whatnot. This cap is more of a permanent thing, which as a labeling, whatnot, but when it's assembled and when it's fully manufactured, they're layered on top of each other. So this is more about, I would certainly want to know, especially medically, if this was a paralyzing agent or not from an end user standpoint, from a manufacturability standpoint, because of the process of how this particular company makes these vials, it can be harder to do some OCR to verify that this text is printed correctly, if that makes sense. Okay.
And what is printed on the metal cap? Was there a follow-on question to that? And that's so it's in the vial.
It's carbon-based ink. from the notes that I was referred to is these are carbon-based inks which absorb it really well and allow us to kind of penetrate that foil layer, something that wouldn't be the case with visible. So it's something with the inks of how it's printed really allow for that, because I don't believe that these are embossed or whatnot.
Okay, gotcha. Another one said, you mentioned coatings. I think different visible LEDs are the same basic LED, just with different phosphor coatings. Is that how SWIR LEDs are made as well?
So that is correct. So it should be, again, no secret that most of the LEDs in commercial things are typically silicon based as well, just like their camera. Another reason we can get certain colors is because we use a fluorescent material to emit that. This is why there's no really such thing as a true white LED. In fact, it's actually really a blue LED that is coated to have more of a broad spectrum. Hence why a lot of white lights still have a very heavy blue concentration. Especially, you'll notice that's why, like, you'll see blue light filters or blue light glasses. With SWIR LEDs, because of the reason that we mentioned talking about camera sensors, we need to make the LEDs out of a different material. And typically the LEDs are going to be made out of an in-gas material as well, to make sure that they're properly emitting that, and as well as using still fluorescent material to then tuning what exact wavelength that is.
Okay. Another one here. When should area scan SWIR be used versus line scan camera SWIR?
1 second, I lost the presentation. Area, and then again, I mentioned this a little bit before, but area scan is, ideally it's going to determine your application. If you're looking at any sort of film or, very line, barcode reading, those applications just are naturally going to be line scanned systems. There are some, where an area might make sense, but like I said, if you have that flexibility, ideally you want to start with line scan, lower cost of entry. You're also going to get much higher resolution, much faster, being able to run it a lot faster compared to area scan. If you're unfamiliar, that's something that, here at Metaphase, we can help you walk you through that, as well as your distributor will have that information. But typically, line scan is going to be cheaper, but again, depending on your application, your mileage may vary and you may only have one option.
I think we kind of already touched on this, but somebody else asked it separately, so I just want to ask it again. Do you have SWIR cameras and lights in your application lab so we can send you parts for your application group to test?
And then that's the benefit of it. I have a whole library of SWIR lights, cameras, and lenses to be able to properly image this and be able to provide information that is crucial for image processing, but also walk you through if you're not sure what wavelengths or type of light you're even going to need for a product.
Right. And then talking about quantum dot area cameras, someone was asking, are they not held to the same ITAR restrictions that you were talking about as in-gas cameras are?
Yeah, so quantum dot is a very cool and developing technology that's we've only seen really some commercial units from some camera manufacturers in the last about 5 years. So it is still very developing. There's a lot of research that goes into it. And the end result is a truly high resolution camera, though that needs a lot more light. If you're looking at something very detailed, that's the benefit. Because of the way the international defense laws and regulations are coded, it is much easier to state that the quantum dot doesn't fall under those restrictions. So that's why they're able to achieve much higher area scan resolutions compared to their in-gas counterparts, because a lot of defense and military organizations have a lot of control over the max resolution allowed for in-gas sensors.
Okay, and we didn't get to your question now. I know we're trying to wrap it up as we're coming up to the 45-minute mark, and I know it's a busy time of year, and I appreciate everyone's time for attending. We will email you out separately if we didn't get to you. And also, if you have any further questions, again, there's our contact information. If it's about this subject or about anything else, we're happy to help you. As I said, we want to be your partners in machine vision lighting. We want to be solution providers. So always reach out to your sales manager or application engineering team or myself. or any of the customer service reps. We're always available, always ready to help. Just want to thank Austin for the presentation, taking the time to put this all together, and thank all of you for your attention and your attendance. And I wish everyone a very safe and happy holiday season.
Yep. Thank you, everyone.
Thanks. Bye.